Okay. I hope we're okay with that because I kind of went through it quickly, but now we can, well, we're still reviewing units of electricity. All right, we'll start with current. And the symbol is I, which stands for intensity. Intensity. Let's see, the conventional current symbol for current is I, which may seem puzzling. It originates from the French phrase intensity I can't pronounce French, or in English, current intensity. It is measured in
amps.
Measured in amps, which was named after Sir Isaac Andre Marie Ampere. It is the flow of electrons. Flow of electrons through a conductor. And I don't know, I got this out of the book. It's the worst thing ever. Like water moving across a water wheel. No, I disagree. It's kind of like more like a pipe. So if we had a pipe, and our pipe is synonymous to what in electricity? Conductor, a wire. And so if we put like a little fan in there, and that little fan, of course, had a little wire coming out, and that told us our flow. That's what that would be like. We have to measure the flow. We have to measure all of the flow. If I were to make a parallel, well, that's weird that it did, make a parallel little pipe coming out of here and water bypassed it, would my flow be correct? No, it would not. So it can't have a parallel circuit. We have to measure flow. Flow is measured in series. All right, so amps are measured in series. Let's see. Definition of an amp. So 1 amp, and we do use a capital A because it's a person's last name. 1 amp is the flow of 1 coulomb per second. And what the heck's a coulomb? It is an amount. So 1 coulomb equals, I just remember it because it's pi times 2, which would be 6.28 times 10 to the 18th power. And I remember it's 18 because it's more than 17 and less than 19. Little memorization tricks right there. All right, so it's O is measured in series. What happens if you don't measure it in series? There is a little device inside of your meter that will help you remember that. There's an indicator. So it's always measured in series. Now, it doesn't always blow. If you have a very small voltage, like if you're trying to measure amps through a load, which is what you should be doing, and you just happen to have a resistor that has a very low voltage drop, it's maybe like 1 volt or something like that, and you put your meter across it, usually it's okay. It's when you have more than that it's not okay. All right, so next is voltage. Voltage, the symbol is E for energy. Electromotive force. Or EMF. That is very different than PMF. Do not get the two confused. No, PFM, that's what it is. PFM? That'd be pure freaking magic.
that what most of this stuff is?
Yeah, we don't know how it works. So electromotive force, because we will see the words EMF quite often come up here later on. We'll talk about EMF, which is, think of it as that. Let's see, measured in volts. Named after Mr. Volta. Alessandro Volta. It is electrical pressure. E-L-E-C-T-R-I-C, electrical pressure. So it is the pressure pushing the amp through. I prefer difference of potential. And again, if I could draw halfway decent, let's see, we have here a little wall. We'll make another wall. And we shall fill these with water. So we have water in a dam. This right here, and this right here. Yeah, water kind of slopes downhill. Let's see. Let's do this right. There we go. Let me think. This is a new concept for me to draw out. Just can't. All right. So it's always the difference of two things. So that's why when we use voltage, we have to measure. We're looking for differences, and we're doing it in parallel, not in series. So difference in potential, and it's measured in parallel. So the difference right here between this water and this dam and this water and this dam would be the pressure between the two. So we'd measure put a probe here and put a probe here and measure the difference between the two, right? And that would be our voltage right there. Or we carry this out over here. Difference between here to here would be the difference between here and here, or the difference between here and there. So the voltage drop. So we have the voltage drop, it's what I like to say it, which would be the same as the water drop. And of course, if we went from here to here, that would be considered what? Voltage total, right? I'll work on that one, but maybe that helps you a little bit. So it's always looking for the difference. And that's why when we take any sort of circuit, and we can say this is 12 volts, and we'll just do a one element thing right here. We can't say, well, what's the voltage right there? We can't say it's 12 volts. It's always as compared to what? What's the voltage there? The next question is, compared to what? So the voltage right here compared to the voltage right there is? Zero, because there's no difference. And the voltage between this spot right here and this spot right here is? 12. Does it have to be 12? Could it be 6?
That'd be problematic because it doesn't zero out.
Not if Ohm's law is correct, or Kirchhoff's law,
Yeah,
which you said is correct. It won't work. You got to drop the whole thing. You got to drop all 12 volts across that resistor. It will drop all 12 volts or break. So one or the other. So it's always measured in parallel because it's the difference of two things.
Could voltage be considered a ratio?
Yeah, why not? So 1 volt will drive 1 amp through 1 ohm. 1 volt. 1 volt will, I'll say, push 1 amp through how many ohms? 1 ohm. A resistance. The symbol is? Symbol is okay. And as the symbol is R and the sign is?
Omega.
Is, I screwed it up. Omega. Omega. That's the worst omega I've ever drawn in my life. That's the second worst. All right. Also known as Lululemons. All right, old joke. Measured in ohms. Named after George Simon Ohm. It restricts the flow of current, causes a drop in voltage. Also thought of as electrical friction. I like that. Electrical friction. What does friction cause? Heat. Ooh, your little tiny resistors, they use up electricity. In what form does it use electricity?
Transfers into heat energy.
Mm-hmm. Just transfers it to heat energy. Those resistors get a little bit warm.
Like brakes on a car.
That's exactly right. Just brakes on them. That's what it does. All right. So a simple circuit. Again, review must contain.
Power. Powers.
All right, power supply. Power supply. What can we consider a power supply? Battery. What kind of electricity is a battery output? Direct current. Okay, what else can we use?
Outlet.
A generator off our engines. Generator output is
AC?
DC.
DC, okay.
Internally it's AC, converted to DC mechanically. Output is DC. What else?
Motor.
Motor's the opposite.
Alternator.
Alternator. What kind of electricity does alternator produce?
Alternator.
Technically, internally it produces three-phase AC converted in a solid state matter through diodes to direct current output.
Because diodes only allow flow of electricity in
One direction, so it uses a rectifier. We could literally use something called a power supply, which is something that would plug into the wall and produce power if we use our circuits, which we will be using here probably this week. Depending on you, Alex. You're kind of leading the pack here. We'll see where you get to. Yeah, powered through it. What else we have? Well, there are AC generators that we could be used. We have the wall outlet, all kinds of stuff. So, all right. Power supply. What else do we have? Must contain one. Power supply. Two.
A load.
A load. What happens if we don't have a load?
Wires burn out.
Yes, it does. They get very melty. A load. What else? A path. Okay. A single path for series and more than one path. So series can only have one path. And parallel, more than, or two or more than one path, two or more. And lastly, we must have power supply, load, path. Well, conductor would be in there, but that kind of works with path.
Ground?
No, not a ground. And we want to be careful with, and I'm glad you brought that up, how we say ground. Because when we're working with DC circuits, our ground is our return path. It's really the return wire. As opposed to AC and our wall sockets that have three wires. The black, the white, and the ground wire, which really is not part of it. That's a safety part. The power goes through the other ones. They're going back and forth through the black and white. The ground's a safety. So it can leak to ground. You don't need it. A lot of homes didn't have it a long time ago.
And then they burn.
All right, let me see. A simple circuit. All right, Ohm's Law. Ohm's Law. Named after Dr. Albert Law. All right, Ohm's Law. We have the units of electricity. Let's just do this. Ohm's Law. So, oh yeah, I put that in there because I'm always trying to explain it. You know, it's like the one show with the thing. All right. Oh yeah, then I threw this in there. That was the Schrodinger model. Uses the probabilities. That looks more like what that is. These are the electrons buzzing around. Then I had to put the cat because it's the same guy to remind me. It's the same guy that did the cat. All right.
Cat.
Huh?
Oh, I didn't see
Down at the bottom.
I couldn't see it on either side.
Looking at it this way, it's not a cat, but that way, yeah, maybe.
Why does it look like my parents fighting?
Cat?
That was funny. Looks like his parents fighting. Oh my gosh. All right. Let's see. So we got the cat. This. Okay. Ohm's law. So we're talking about Ohm's law. Yes, we are talking about Ohm's law. All right. There. Ohm's law. So we have the Ohm's Law Wheel, and the wonderful thing about the way this class. Well, I'm the one that kind of came up with most of the stuff. But the way you can deal with the tests, all of the FA test questions, as we've already discussed, is you can do this entire wheel into E, I, and R. And you can solve every single problem with EIR and PIE. Really, you can do P equals I times E most of the time. I don't even think you need the triangle. But there's so much more to it that you could potentially use. It just doesn't come up in the way the FA test questions are written that you need to know all of this. And I don't even think that they actually give this to you on the test anyway. So it's not difficult to memorize this. You're going to accidentally memorize a lot of stuff just through usage, which is the way it should be. But just know that there's a lot more to Ohm's law than the simple EIR that we're using and the PIE that we use. But between these two things, if you can memorize those, you're going to do fine. You'll pass every one of my tests, and you'll pass all the stuff on the FA test. But there is the other formulas that you could do. And these come in very useful when you're given EIR and power, and you're given some sort of power, and you're missing a component up here that you would normally need. We said 10 ohms. Let me think. Yeah, you might have trouble with that one. It's like, well, I don't know I and E off that one. But you could compute it off of this wheel here. But it just doesn't come up in this class that you would have to. So that is the good news. All right, back to this. So Ohm's law. Ohm's law, that is Ohm's law, which we all know. At this point, EIR, and we just make the triangle. And if you want to know one thing, just cover it up. So E equals I times R. R equals E divided by I. And I equals E divided by R. And again, I've said it before, I have no problem with you writing this on the top of every single paper that you're working on. Just put a little EIR on top of the paper if that's what you want to do so you can reference it. I'm happy with that. And then, of course, we do pi. PIE, so P equals I times E, or I equals P divided by I equals P over E, or E equals P divided by I. All right. All right, so speaking of P and pi, we do have power. Power is expressed as? Power. Power is expressed as the watt. Watt. 1 watt equals 0.00134 of a horsepower. 1 horsepower equals how many watts?
743.
746 watts. Where did this come from?
Wasn't it like how long it takes a horse to pull a certain weight, a certain height, or something?
Yeah, he's onto it. I don't know if I have this story exactly correct, but Mr. Watt needed to sell this newfangled steam engine that he'd created to the mining industries. And so he had to convert it. Hey, I've got the steam engine. It does work better than a horse. Well, how much better? Well, is it an English workhorse comes into play somewhere? So it has to be an English workhorse. It can't be some other nationality. And it can't be a show horse. Yeah, yes. So it's very, very specific. It was an English workhorse, if I have the story right. And it was the amount of energy to raise 550 pounds. So 1 horsepower, one horsepower was the amount of work to raise 550 pounds, a distance of 1 foot in 1 second. So it came up with this fancy way of saying, okay, my engine can do this, and so that's kind of how he was selling his engine. So the guy was a good salesman, is what I take away from that. So anyway, that is, what's that? Or what?
He picked a really shitty horse.
I would if I was, So it's probably why it had to be an English workhorse. They're on T-brakes all the time, You get German workhorse, the guys never stop, And then there's the Joule, which I don't know. I wrote it down here. I don't really know where it comes into play. G-O-J-O-U-L. Joule. A work done by, it's 1 watt in 1 second. Or approximately 0.3736 foot-pounds. No, it's not on the test. All right, and in 309, we did talk about the dangers of electricity, which I don't believe it's on the test, so I don't really need to go over it. Anybody remember what the... I hear you digging through your 309 notes. I'm going to answer this question. I don't even remember it offhand. Let's see. We'll just review real quick. Callous dry hand. Let's see. More than 100,000 ohms because of that thick layer of dead skin cells. So if we have our ohm meter on, we have it on the times 10,000, and we're hanging on to it, you're going to see a reading on there. So when you have it on that scale, try not to touch. Otherwise, at that point, you're actually creating parallel circuits because it can measure you and the component you're testing. I do also see a lot of you when you're measuring your circuits, and I'll say, okay, what is the amperage of that? You will grab onto things and hold it, and that's fine for now. You're going to want to break that habit eventually, but you won't need me to tell you when it's time. Let's see. So internal body resistance is only 300 ohms. So let's see. 1 milliamp would be like licking. Yeah, 9-volt battery. I give out a little bit of tingling. 5 milliamps accepted as the maximum harmless current. That is so little. That's what we're dealing with right now, right? 5 milliamps. It's just that our skin has got so much resistance that if we did the EIR on it, I don't remember what we're getting. You're just not going to, huh?
7,000 or something like that.
I think it's way more than that. So even according to this, a callous dry hand may have more than 100,000 ohms. So if we said 100,000, 100K, so we did EIR, we're only dealing with a 6-volt battery. So at 100,000, what's the maximum current we're going to get? So for those of you who weren't paying attention, it's E is IR, so I equals E divided by R, so 6 divided by 100,000 would be like, how many zeros?
0.06 milliamps.
0.06 milliamps or 0.00006 amps. So we're a long way from there. If we could break it through and get to if you get stabbed with one of these things, and now you've got your, a resistor stuck in you, and we put some power to it, we're down to only 300 ohms at 6 volts. What do we got?
20 milliamps.
20 milliamps. So that would be
4 times above the safe level.
There we go. So don't do that.
Don't stack yourself.
Don't. Yeah. If you get stabbed with resistor, don't hook it up to your 6-volt battery. 10 to 20 milliamps, muscular contractions and ability to let go. 10 to 300 milliamps. That's 300 milliamps. How many amps is that?
0.3 amps.
0.3.
That's permanent damage?
We will be dealing with often. So once we get to the motor project, that's going to be taking close to 10 amps. Then we're going to move on to batteries, which have 450 amps. Then you'll be working on a ni-cad single cell thing that has it's 24 amp hours, I think. So that's 24 amps for an entire hour. Or instantaneous would be, I don't know, a couple hundred still. So we're going to be getting up there into the amperage series, amperage. So I think your biggest risk is going to be burns from hot things. So we're going to get stuff that some resistors are going to be using are going to get hot enough that you'll smell them burning in the classroom. And that's going to be normal for the project we're doing. They're dissipating a lot of heat. All right, so let me see. Series requirements.
How long can they sit there after getting, I don't know.
We're going to do battery discharge tests. And so you're going to be using very large resistors that are not that big. So,
Whoa.
yeah, they're made to do that. They're going to get really hot. But I'll have you like prop them up so they get some air around them and circulating. You'll just smell them getting hot, but they're
They
that
can
way.
sit there and hang out hot.
I think they're 25 watts, if
Okay,
I remember
but
correctly.
they can just like sit there and hang out hot for a while.
I just don't do. Obviously, we'll be dealing with batteries, which will have acid component to it. At that point, you won't want to wear clothes. I've ruined so many clothes from the batteries. In fact, I just changed a battery in my airplane. I just have to throw away a set of clothes every time I do it. So anyway,
Sell them as fashion items.
I know.
I don't know why.
All right.
Buy them at a price and I'll sell them for more somewhere else.
All right. I don't know why we are talking specifically about series circuits. Series circuits, and I have the requirements, which we already went over, which was one path, load, power supply, all right, the conductor, power source, load, only one path. And then we get into, I don't even have it written down here, and Kirchhoff, and I say it Kirchhoff, it's Kirchhoff is, I believe, the correct pronunciation. Which somebody once told me, never ever make fun of somebody the way they pronounce something, because more than likely they read it in a book, which means they're a reader and they made up the way they said. So don't make fun of them because they're probably smarter than you, because they're a reader. Oh, it's 2H. That's it. 2 H's, 2 F's. Kirchhoff's laws. So we did cover this before. And I'm kind of starting to realize, or learning through reading some other books, that the way that, now it's hard for me because I want to say it the right way now, Kirchhoff, I can say it any way I want, you'll be fine with it, right? He's gone, he's dead, he won't care. The way I teach it, the way the FA book has it, is not necessarily what he said. And in fact, it's very confusing at first with what he said. But let's start with this one, where voltage total equals, in a series circuit, voltage drop of component 1 plus voltage drop of 2 plus voltage drop of 3, on and on and on. And I love that. And for me, that works in my brain. I don't know, it's because of the way I originally learned it. But it actually goes something like the sum of all voltages equals 0. And to that, I'm like, what? And so you have to demonstrate it out. Just so you know. I'm sticking with what I just wrote, but I want you to. So if we put a voltmeter this way, and I got to use the right colors here, so red, this side's got to be red, and this side is red, this side is red, okay, black. So we have black here. And let's say this is 12 volts. I shouldn't have done that. Yeah, okay, be fine. How many volts will this say?
12.
Okay, it'll be on a digital meter. What will it read? It'll read positive 12 volts. And I already screwed this up. That can't be there, that can't be there, that can't be there. Moving around in the same way, I would have the red lead this way. So it's red lead is like this, and I never move hands. Red lead, red lead, red lead. See how you never left hands. Red lead is always going to be on the right-hand side, except down here because it's upside down. So this would be, and let's say these are all the same value. So if all the resistors is the same value, then this would be
-4.
-4 volts. This would be
-4.
-4, and this one would be
Negative 4.
-4. So positive 12 minus 4 minus 4 minus 4 equals 0. So the sum of all voltages equals 0. Yeah.
Just for the sake on the series parallel test, it's the exact same thing, but they say that the battery's negative, but it's the same thing. It's just in case somebody gets confused later.
What?
So on the series parallel, on that it talks about Kirchhoff, however you pronounce it.
Oh, in the textbook?
And no, not in the textbook.
On that
On
program.
on the computer, when you look at the examples for
Oh.
the series parallel, it's the same, but it's negative, and you're adding the resistors instead of subtracting the resistors.
Okay.
So it just, I was looking at that before, and it didn't make any sense, and I look at it here, and this makes more sense. So
The only reason why I bring this up, and it doesn't play into this class, but I now see where you get into complex series parallel circuits. This works even if you don't do the whole circuit. You can do part of a circuit, and as long as you make a circle within that circuit, it's going to do that. And I don't have a real good example for you without drawing this complex series parallel circuit. And again, it doesn't even come into play in this class. I guess it would be something like that is a series parallel circuit, right? There's things in series, there's things in parallel, and we'll get into that later. But the point was you can do the voltage across this, the voltage across this, the voltage across this, and you can come back around and you can use this circle here to kind of do the same thing, is what I was saying. But that's not really in this class. It's not something I expect you to understand. It's just if you ever see that is an alternate way of Kirchhoff's laws. We're sticking with this right here. Voltage total equals the voltage of 1 plus 2 plus 3. It will work every time in this class and for all FA tests, and it's not incorrect. So current, Kirchhoff's law for current is I total equals I of 1, which equals I of 2, which equals I of 3. Very good. So it is the same. Current is the same. Current is the same for the entire circuit. What if it's not the same?
And it's parallel.
Well, what if I've got this and okay, we got to do it in series, so right there. What if I had 2 amps there and I'm over here somewhere and I figure out, oh, wait a minute, this is more like, 3 amps. Then what?
Short.
Well, first of all, if you have 2 amps flowing right here, where'd you pick up the 3rd amp?
From an outside.
Outside could be an outside
Hot.
source.
Hot
All
or
right.
cold or something like that. Temperature?
Is it possible for this to happen in a circuit like this?
I don't know. Probably not. I don't know.
Yeah, I'm gonna say you made a mistake. You made a mistake.
Huh.
This isn't gonna happen.
I thought this was a trick question. I was like,
It's not.
"That's an idea."
People get it all the time. I get people checking out. Well, I got 2 amps here, but 3 over here. Well, no, you don't. In a series circuit, whatever you have right here is going to be the same here, which is the same here, which is the same here, which is the same here. It's got to be the same. If it's not, then you've got to break off somewhere else, and you've got another parallel circuit going on to steal it. Otherwise, it doesn't work that way. And of course, all of the voltages, as we talk right here, must add up. They must add up. If these voltages right here, the voltage drop across this resistor, the voltage drop across that one, the voltage drop across that one, don't equal the total, then
you did it wrong.
you did it wrong. Okay. So let's go back and look at that. So one of the things that I'm really hoping that you do, and I can't force you to do it, is to think about what it is you're doing when you do these projects, especially these simple ones, because they're going to help you so much when we get into more complex ones. Just if you think about what's really happening. And as we talked about earlier, if we kind of examine this spot right here, this is a 12-volt battery, how many volts are right there?
Compared to what?
Compared to what? Right? It's like, I don't know. How many volts are right there compared to right here?
0.
0. That's a hard concept for people. It's like, so you mean there's no pressure there? Well, yes, there is pressure there pushing electrons through, but you're not comparing it correctly. So the question is, there is pressure, but compared to what? You know, compared to right here, well, then there's 12 pressures. You know, but if we're measuring it from here to here, then we're measuring
Voltage drops.
the drop, the difference between what the voltage is over here in this area versus the voltage over here in this area. So, you know, really think that through and try and get that into your mind about, okay, it's the difference between here and there. Because the next thing is people go, wait a minute, what if I'm measuring it going this way instead of the other way? Well,
Negative.
it doesn't matter. Well, it'd be negative if you just swap the leads, but so what? You know, it doesn't matter.
It'll beat up the reader.
Yeah, but not if it's digital, right? So it doesn't matter if it says +6 or -6. Difference is 6. It only matters on the analog because the meter doesn't go backwards. If I'm using a digital meter, I pay no attention to which way my leads are going. If I'm not troubleshooting something that could be potentially backwards, I don't care. Or I do care, and I just look at the meter. I just put it on and go, it's -6, so I got the things backwards. I don't care. 6 is 6. Doesn't matter. That's the way I look at it. All right, and then of course, last thing in Kirchhoff or series is resistance equals R1 plus R2 plus R3, which is to say that all of the resistances add up to the total resistance. But you already knew that because all of you have already done a series circuit and done it well in 309, and most of you have already completed it here. So this would normally be the time where I would take a lot of effort and energy and do a whole bunch of these things with EIR and let you walk through it and experience EIR and how to fill this out. But I feel like everybody here has already done this, and if you haven't, because
How are you here?
no, we have 2 people who are here differently than most of you.
Oh.
Yes. So Vlad and Arlene, just trying to remember which last name to use, but I came to us during engines. So they've already had engines. So they started in different spots. So 309 was a long time ago for them. And they've already completed 1 semester. So they're in their 2nd semester. And so next semester, when you start engines, they'll be outside with the big kids. They'll be at the big kid table,
Very cool. We back with our friends.
I think. Okay.
Is this, was that like what was it, you were talking about different starts of the program?
Yeah.
Like
Yeah.
the winter start versus this.
Yep. And then there are several people who took 309 this last summer who said they're going to start in January. So we'll have some new people in here with you, but not too many. All right. So if you guys need any extra, like, hey, go over this, just let me know. But I gave you a lot of examples to work with in Canvas and the answers. But I'm available, and some of you are taking, this is the first class that's ever really taken much advantage of office hours. As you know, I'm sitting in here. I'm usually, but today I got here at like, I don't know, 1:30. So, yeah, come on in. Ask me questions. Huh?
Available at 1:30?
Sometimes yes, sometimes no. Like today I wasn't. I ate lunch and, chilled out, took a nap. I did not take a nap. All right. So let's talk about parallel circuits. This is going weird. I'm like on day 4 stuff now. We just blew through this. Okay. I'll have to think of something to do. All right, so parallel circuits. We have the same requirements. More or less. We must have a conductor. We must have some sort of load. We've got to have 2 now. Because you only have 1 load.
It's serious.
It's a series. You can call it parallel, but it's not. We, of course, have to have our power source. Power source. And more than one path. More than one path. Within a component, you might find series or series parallel circuits, but outside of a specific component within the aircraft, almost everything is going to be a parallel load. Everything is parallel. Like I showed you before, you have one wire that's going to run to the bus, then off the bus, you're going to split off everything else. Even if it's one switch to operate something. So let's see, we have the bus. What comes right after the bus? Yep, circuit breaker. The only exception to that, and if I put a little thing like that, it's resettable. Only exception to that is starters don't have circuit breakers in aircraft. You just don't circuit break it. All right, then the next thing to happen is a switch. So I have one switch that operates 3 lights on my aircraft, the nav lights. You got a red one, a green one, and a white one. And so I guess they could run it like this, right? Red, green, white.
But then if one goes out, they all go out.
One goes out, they all go out. Well, then it makes it easier to, no. So you can't do that. So
You put it in parallel, so if one goes out, there's still what's the word? It starts.
The circuit?
yep, so it's going to come off of here and parallel. Well, let me do
There's
this.
still continuity even if one breaks.
So it's going to go, yeah, we'll do it like that. One that way. One this way. One this way. And each one will be grounded out at its spot. So that would be the proper way of doing it. So I guess in a way you could say it's series parallel. The lights are all wired in series with the switch, in series with the circuit breaker. If I thought my lights were unusually dim, maybe I have one dim one, what would you do?
Bad ground.
This is bad ground. But what do you mean by bad ground? What is the ground?
The ground, so there's a hot wires are generally the wires that's going to run to whatever component you have. And the ground wires may be shorter, going directly back to the airframe. Or in the case of a light bulb, maybe the socket is the ground, and that's kind of corroded up, and there might be that's partially part of your ground.
Okay,
But it's
he's correct. But I want you to picture kind of how airplanes are. So remember, airplanes are sometimes combination metal and plastic. Well, cars are more that way than anything nowadays. But like my particular aircraft is a metal aircraft. It has plastic fiberglass wingtips. Fiberglass or plastic, depending on the model. And so out on the plastic wingtip, I have a nav light out there. So I have one wire that's going to run from back of the instrument panel, right where that little switch is. Going to start there, run along the instrument panel, up the post, all the way out to the wing, go right to the bulb, to the little fixture the bulb screws in. There's one wire right there. And then there'll be another wire that's usually soldered on to the casing of where the light bulb goes into. And that's about a wire about yay long that's going to go back and just screw right into the wing. That's about that long, just screwed to the wing. So in reality, the power is coming from the battery, going to the airframe, going around the entire airframe, finding its way out that wing to that little wire, to the light bulb, and then back through to the switch and the battery, right? But that sounds stupid to say that. So it's so much easier to say, no, power comes from the battery up that big fat cable, goes to the master solenoid, goes to the bus bar. From the bus bar, it goes to a circuit breaker, switch, then a wire up, over, out to the wing, powers the light bulb, goes back yay far to ground, and it goes back out. So if I have one bad bulb, generally speaking, it's not that power wire that's going out there, because if it was the power wire had a problem, the problem is usually it eats through a piece of metal or something. Then what do we have? A short, and a short usually results in
No power.
fire,
Or
Smoke.
circuit breaker
Pop circuit breaker, because you're taking too much of a load. So the circuit breaker, and we'll get more into this later, so I'm not writing it down because I'll write it down later. Circuit breaker is there to protect the wire, not the light bulb. The wire. That's a big deal. Those are test questions. So circuit breaker protects the wire. It's designed based upon the wire size. But Evan said it's a bad ground. Well, it just so happens in life that little screw right out here that screws that wire to the airframe, that tends to be where you get corrosion because there's no, and a lot of times that happens. So, all right, what if all three of them are dim? Unusually dim.
Bad switch. Yeah, you
Might have a bad switch. And so I say, all right, I might have a bad switch. Well, what does it mean bad? I mean, the lights go on, the lights go off.
Maybe the connecting point is corroded, so it's not making a full connection.
So what does that mean if it's not a full connection? What do I have?
Less than full power.
Well, what's causing that?
Resistance.
That's what I'm looking for. You got a resistor built in there somewhere. Do you want a resistor there?
No.
All right, so how are we going to figure out if that's the case?
Bypass the switch.
What's that?
Bypass the switch.
Sure, you could bypass the switch, absolutely. Just take a nice piece of wire, bypass the switch, screw it in there. But let's just think
Check the
ohm
resistance
meters
of
and stuff.
the
Yeah.
Switch. itself.
All right, that's what I want to hear. Check the resistance of the switch.
Between poles.
So let's say I take the switch out, and what do I use?
Use
Ohm meter.
Well, I could say I could take the switch out because we can't check resistance with a load, so we can turn off the master switch. It'll be fine. Be aware, though, when the master switch is off, it does not kill all power to the back of the panel. There's always, like I have an electric clock in my airplane that takes power from the battery through a little tiny fuse all the way up and through. And now with all these electronic instruments now, there's power wires feeding those. So there's power back there. If you forget, you'll learn it the hard way.
Isn't there like power to like storing, like helping to store memory within those electronic?
That's what I was saying. Mostly they have internal batteries now on their own.
Okay.
Mine does. So, but my clock has a power wire up there. Oh yeah, I think I got a power. Yeah, I did run some power wire for like some other stuff now. So yeah. Anyway, the point I want to get to here is, all right. So we could turn off the power and we could measure ohms from this wire to this wire, right? And sometimes, oops, wow, this is such a great thing. Sometimes that works, but not very well. And let me tell you what works way better. Power the circuit and do what?
Use Ohm's law to calculate the rex.
Use Ohm's law. You'll be surprised at how much better that works.
To check the voltage and use Ohm's law.
Check the voltage drop. You will pick up ohms where you will never see them before. Your little wires that you guys have that you're going to be doing a lot of stuff with, they have a fair amount of resistance. You can't measure it with an ohm meter, but start putting some power on them and you're going to see a voltage drop. So when I say to you, hey, how much resistance does that wire have in the circuit? What are you going to use?
Use the voltmeter.
Use a voltmeter. We'll talk about that tomorrow. So.
That's cool.
If you go back to the Schrodinger's